Okay. Okay, to continue with this exercises, today we will do something on push down automator. But this is perhaps the only question on context-free grammars. So we will later go to push down automator. So consider this language. Set up all strings over the alphabet A comma B such that the number of A's is exactly equal to 2 times the number of B's in X. So first design a CFG for L1.
So we can do something which is like uh, S maps to AABS or AASB or ASAB, and like we add an AAB or ABA or BAA, one of these three, and then we have S maps to SS and S maps to epsilon. There will be a lot of redundancy, but this should work.
Okay, so I leave it to you to prove whether this suffices or not. Yes, I know this is the first suggestion that will come from you. So I have actually something a little bit different in mind. So prove or disprove whether this is sound and complete grammar. Of course, it's not unambiguous. That is fine. A B S A S B A S A B S A B and other things also like BAA or ABA and so on. Then put ACR, 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 or for all permutations of double AB. And eventually you say SS. Okay.
Or the S at the extremes can be easily derived by SS and then the S at the middle. Like AABS is come like evidently like redundant.
Let it be redundant, it doesn't matter. We are not worried about redundancy for the moment. First question that arises, I will think over it, but Question is whether this grammar is sound and complete. Okay, sound means, of course, soundness is almost obvious because the way we are writing these rules, it makes clear that it will only generate strings in L1, but are these rules sufficient to generate every possible member of L1? So that is completeness. So I leave it to you as an exercise. What I want to show you, there may be some problem. I have not thought about it. So we will see. Yeah, you figure out. I don't want to think about this. Okay. What I will instead do.
Sir, the string triple A, triple B, triple A, does that string belong to this grammar?
Triple A, triple B, triple A. You tell. Possibly not, right? Possibly not.
Yes, sir.
Yeah. So it's basically disproved, right? So this cannot be generated. Good. Anyway, you solve this. Okay. Yes, maybe. Yeah. Okay. Anyway, so I have another thing in mind. So now I will define surplus of X to be number of A's in X minus 2 times the number of B's in X. Okay. And S will generate all X such that surplus of X is 0. I will use two other things. A, this will generate all X such that there is one extra B, one extra A, and B, where the surplus is minus 1. But now it is not the surplus of A's over B's, surplus of A's over twice the number of B's. Okay, and now let us look at that surplus curve for S. Overall prefixes. Initially the surplus is 0. Finally, it will also be 0. Okay. So rules for S. Okay, if I read one A, surplus increases by 1. If I read a B, surplus decreases by 2. Okay. So if an A comes, it will be this. Whereas if a B comes, it becomes minus 2. Okay, so S can be definitely epsilon, or if the string starts with S, then what will follow?
B, something in B.
And if it starts with B, what will follow?
AA.
A, right? So increase in this surplus function is like a continuous function. If it is -2 and it will eventually reach 0, at some point it will have to reach -1, and at some other point, and eventually it will reach to 0. Okay, so B, A, A. So that's all for S. I should also add rules for A and B. Okay. So rules for A. So now what will be the surplus function? Starts from 0. It will end up in 1. Okay. So A can be if we start with A,
Then S.
if we start with B,
3 A's.
3 A's, right? B means -2, and then you want to reach 1, and 1 by 1 we have to reach that. So 3 A's. I do not need A can be A because of it can be AS and S can be epsilon. Right. I can generate a single A. The most difficult part is the rules for B. So this thing is like this. Start from 0, it will end up in -1. So B can be okay. The simple things first. If I start with a B, surplus becomes -2. Then this will be followed by
And A.
A. Okay. Now a trouble comes when so this is starting with B, this is starting with A. From +1, I want to end up to -1.
So this can be done by 2 B's or an S, small v, and then another S.
So you see that this decrease in the surplus value is not like continuous. Okay. So it is possible that it at some point of time, it may become 0 and then this. So this is a possibility. A, B, B. That is a possibility, right? Somewhere it comes here, then goes here. But it is also possible that there is a jump from +1 to -1. This decrement is not like continuous function, right? If it is the case, what will be this portion?
Yes.
Yes. This should be by a B. Then once again, an instance of S. Happy?
Yes, sir.
Okay. So this construction will not work as this counterexample suggests. But if you want to make a construction, have some mathematical formulation in mind. Okay, like this. Okay. And if you have that in your mind, then working out the remaining parts is fairly straightforward. Okay, the way I have generated this grammar does not require any additional proof, right? because it's generated based upon this proof. Okay, good. So now we will do two things. First thing is, if I want to I want to generate a PDF for this language. So since now I have a grammar in my hand, I can mechanically convert that to a PDA. Okay, that conversion procedure we have seen in the last class. So you tell me, there will be a single state. We will call it star. That is the start state. And a loop with many transitions. First of all, you tell me, this should be there, right? If A comes, and on the stack, you see A, pop it. Likewise, if B comes, pop it, provided that B is also sitting on the top of the stack. What are the other rules? So you have to convert these things, right? All these rules. How many? 1, 2, 3, 4, 5, 3, 8. It's 8 extra productions you need to add. So what will you do with the production S can be epsilon? What happened? No suggestion? So you are trying to
So we
imitate.
can do an epsilon transition,
Yeah.
which
So you are
adds
essentially,
S.
yeah, you are essentially using the stack to emulate or imitate the leftmost derivation process. So derivation replaces S by epsilon. So you replace S from the top of the stack with epsilon. You may also replace S on the top of the stack by AB or BAA, right? So do not read anything from the input, that if you see A is on the top of the stack, replace it by the right hand side of the rows. So for S, I have 3 rows. What was that? AB and BAA. I also have this row, BAA. Then these are all epsilon transitions. And if you see A on the top of the stack, you can replace it either by S or by B triple A. And if you see B on the top of the stack, you may replace it by any one of these 3, BA, ABB, or ASPS. ASPS. Okay. So given a grammar, generating a PDA is fairly straightforward. Okay. Happy or not?
Yes, sir.
Of course, the converse construction, that is from PDA to CFG, this is not so easy, and we have not yet talked about it. I will do it in the next class. Anyway, okay. So this is one construction given a grammar. But if I want to generate a PDA without any CFG, just from the scratch, what will you do? For PDA, that will keep track of that surplus function in its stack. What should we do? So for every A, it reads the surplus function increases by 1. So I have to make +1 in this stack. And for every B, the surplus function reduces by 2. So I have to essentially subtract 2 from the stack, right? So what I will do, you tell one by one. Possibly I need another state, so let us for the moment do this. First of all, let us consider the situation that an A comes and the bottom marker is exposed. Then what will you do? Tell me.
Push A.
Push A or plus, let's say plus. I will put plus. A comes. You already see a plus. You will push another plus. And if you see a minus, just pop it. So handling A's is fairly straightforward. But then you have to do handle B's. Of course, minus minus this. If you see a minus, this is also fine. Replace it by 2 additional minuses. But if a plus comes, what will you do? If
So
plus, if we can.
So we can make another state, and then we can use a transition over there, and then we can do an epsilon transition from that state to this state.
Okay, good. So if a B comes from in the input, and you see some plus on the top of the stack, okay, you do not know what is there beneath this plus. Okay, it may be the end of I would say what is that called, bottom marker. Okay, or it may be another plus. If it is another plus, it's fine. But every transition looks at only the top. Okay. So one way of solving this is this. I will temporarily go to a new state. So I read B, C plus, epsilon. But then this is a subtraction of 1. Another subtraction I have to make and go back to this state. What would the rules here? This will be an epsilon. If this is exposed,
then minus bottom marker.
minus marker. If another class is exposed,
Just pop.
just pop it. Okay, and eventually you should be able to clear this stack. Here I have another epsilon transition. Replace this by epsilon. Happy?
Yes, sir.
Yes,
Oh.
sir.
Okay. Okay, but I do not know. Maybe with a little bit of effort, I do this thing. What is the third one? Oh, I see. Okay, these are all good exercises, but anyway. Okay, maybe let us do 2. And if time permits, I'll solve problem number 4. It's very interesting. Okay, so now the number of A's is sandwiched between these two quantities. Number of B's and twice the number of B's. And if we have a thing like this, surplus function apparently is not very useful. How do you define the surplus function? Not very clear, right? But we can still exploit the power of guessing that PDA always possesses to design a PDA, right? How? Let us do this thing. Suppose that the number of B's is K. Then what does it say about the number of A's? It is sandwiched between K and 2K. Okay, so I can.
Sir, when we read a B, can we make two possible epsilon transitions to non-deterministically choose whether to do one minus or a minus minus?
Okay. Yes, that's the idea. So this can be written as K plus L, where 0 less than equal to L less than equal to K. Okay, so that means how can I write it? This is fine. I write it this way. L plus K minus L plus L. 12 K minus L. So K minus L is also in this range. Right. So on some A locations, I subtract 2. On the remaining occasions, I subtract 1 for B's. Happy? So I should add some additional transitions to this. So this is for exercise 3. Instead of 2, you are also allowed to push only 1. minus. Here, for this part, what should I do?
So can we add a third state?
We did third step. This extra addition you are just avoiding. You just add this.
Yes, that will be done in this state only. Yes.
Yeah, this state only.
Okay, sir.
Okay. So when you see B, you may choose this path and plus at the top of this stack, you may choose this path or this. Okay. So that will settle this. Okay. Good. So extra transitions added in red. Okay, whatever. Okay, so this is the thing I mostly leave to you. You know this language, A power n, B power n, C power n is not context free. But it turns out that its complement in ABC star is context free. So once again, you see an instance of the fact that context free languages are not necessarily closed under complementation. So how do you proceed?
So this will contain all strings which will have either a BA or CB or CA.
Good. That's all.
And then A to the I, B to the J, C to the K, where one of I, J, and K are not equal to the others.
Oh. So this consists of the following types of strings. Strings containing BA, strings containing CB, strings containing CA, and strings of the form A power I, B power J, C power K, such that I is not equal to J, and A power I, B power J, C power K, such that J not equal to K. K can be arbitrary here. So I only have to match I's with A's with B's. There should be a mismatch. And here I have to match B's and C's and see they have different counts. I can be arbitrary. So this can be done in a context-free manner. Look at this only. Look at this only. Okay, so I leave this details. And again, you see that PD are non-deterministic, so it can guess beforehand which case it is handling, and it will proceed appropriately. Make an epsilon transition to case 1 or case 2 or case 3. Each case has a different machine. In fact, 1, 2, 3 are essentially regular, but 4 and 5 are not regular. So I have 4, 5 such transition diagrams, and initially there is an epsilon transition. Okay. A guess which case it is going to handle. This one, this one, this one, this one, or this one. Okay, so you complete the construction. So let us look at this final exercise of today. This is really difficult. Let L be a context-free language over some alphabet gamma. I consider all strings in L and give it a cyclic shift. XY becomes YX. In particular, I can take X equal to MT or Y equal to MC. So that means L is contained in cyclic shift of L, but it may add additional strings in this language. The question is, if this is a CFL, this is also a CFL. I don't know, it's very difficult to prove in the grammar level, but if you have PDA, it is also difficult to visualize what is happening, but still there is a hope. Anyway, let us see what suggestions come from you.
If the PDA accessed by, let's say, empty strings, then before reading XY, the bottom marker was exposed, and after reading XY, also the bottom marker was exposed. So when we read a cyclic shift L, that will not work. Now, before Y and after X, the same thing would be exposed, but we don't know what is in the bottom of the string. Yeah.
Okay, so first of all, since L is a CFL, there is a PDA for it. And you can make any reasonable assumptions of that PDA, on that PDA. Okay. L is the language of some PDA, let's say M. And you can assume that it accepts by empty stack. It's actually a good assumption in this context. Final state assumption is not necessary. And you can also assume that it has only one state, that construction we have not yet seen. It doesn't really matter.
Sir, can we assume that if L is CFL, then the reverse of L is also CFL? Then we can have the PDF for reverse of L, and then we can initially store Y in the stack, read the reverse of Y, then store X, and then read the reverse of X, and that should be
There is no reversal here. It's a cyclic shift. It's not reversal.
okay, sir. Yes, sir. Yes. Sir, but if we store it in the stack and then read it by popping one by one, then it becomes a reversal, right?
No, there is no reversal involved here. No string is reversed.
No, sir, but we can use that to construct a PDA. Like, if we have the PDA for reverse of L,
Okay.
then we can basically check if XY belongs to L by checking if reverse of Y, reverse of X belongs to L.
So this is the suggestion. So what is reversal of this?
Sir, no, sir, we are just reversing XY. So, sir, we
Whatever.
will have two states, one which will read Y and then compute reverse of Y, and then the second state will read
Compute where? Where? How? Only one place you can compute, that is in the stack.
yes, sir.
Okay, I will not say that this idea will not lead you to something useful. It may. It's not immediate. It's not immediate to me. Okay, so time is running short, but anyway, this is a very tricky exercise. So let us see the working of this machine M on XY, because this is in L. So it is S, some start state. Okay. Of course, you may assume that there is only one state, but it's not needed. Where it reads X, the stack has something. And maybe the state is P. Then it reads Y. Stack is empty. And it is in some state Q. It's possible that S is equal to P is equal to Q. Okay, so it accepts by empty stack. So if it additionally accepts by final state, then Q will be a final state, but it doesn't matter. Okay. So this is the working of M. But now N will start reading Y first. So it has its own bottom marker. It will have something here. Then it will read X and will end up with an empty stack. So what is missing from N? This portion of the stack. Agree or not?
Yes, sir.
Otherwise, everything is fine. Okay. So the missing part here is this stack. Instead of this, it has this, its own bottom marker. I can use the same bottom marker actually, doesn't matter. But note that N is also going to be a PDA. So the idea is that it can guess this part of the stack. Okay. And so it just, let's say it guesses what is there in the top of what is there in the stack. Okay. Then it can somehow continue reading Y. But in that case, what will happen is that this will end up with an empty stack. Okay. It cannot proceed any further, right? If it makes just a guess of this thing, and then it reads Y, it ends up with an empty stack. It can also guess the state P. Okay, and then it will imitate this M, but it will end up with empty stack. How will it handle X? The idea is this. There should not be an empty stack here. And this is basically a validation stage. So when you read X, essentially follow the working of M, but alongside that, you somehow have to prove that whatever you guessed is correct. So if you guess something like this, at this stage, you should be confident that, yes, whatever I have guessed is correct, and that is the reason why I am able to empty my stack. So it will guess certain things and remember the guesses in the stack. And this is the validation stage, which will essentially I would say verify that the guesses that I made are correct. Therefore, I am able to empty my stack by removing the guesses one by one. Okay, so this construction is not at all obvious. I do not know how to. Okay, let me first give you a generic description. Okay, so what N does, it replaces this. This is an initial epsilon transition by some symbol, maybe some separator. Okay, it's a like lid. Okay, so let me use this symbol. Okay, very long dash. So it's a kind of lid. Okay, then what it does, it looks at a transition. If that requires a stack symbol A, it momentarily removes this lid. Anyway, you have this. Guess that A should be on the top of the stack. So remember this guess below the lid, and then have this A on the top of the stack. Now it imitates N or M. M requires, let's say, A on the top of the stack. Okay, and it replaces it by something, something, something. Okay, it does similar thing. But it also remembers that at this point, in order to proceed, I remembered an A. Okay, and this thing goes on. Let's say on a future instance, the lead is once again exposed. Okay, situation is like this, and in order to proceed, the original machine now requires another stack symbol, let's say B. So what it does, it momentarily removes this lead, guesses B, A, this, put back this lead, B. And now it sees B on the top of the stack. So it can now proceed as the original machine does. And you see that the guesses are one by one stored. Now at some point of time, this PDA assumes that it is done with that guessing stage. Okay. Then what it does? It assumes that it is done with this guessing stage. So it's done with this part. Now you have to go to the verification or validation phase. Okay. So once again, you imitate the working of M, except that instead of this, you will see this lead and introduce stack symbols as M does. Whenever you do so, again, non-deterministically remove the lead and see whether this guess matches this guess. If so, remove this guess. Okay, and so on. Complicated, right? I think you need an example to illustrate this, but it's already 9:02. Okay, so will you think about this? Okay, so what I suggest as a homework, consider this grammar. And let's say we take some string like this, A, B, B, B. And a possible cyclic shift is A, B, 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 A. Okay. So how will this new machine imitate this using these two phases to recognize this? And even a better thing is set of all even length palindromes, let's say. Okay, so you try to work out how this construction can be made to work. Okay, so let us stop because it's already 3 minutes past 9. Should have other classes.
So can we do something where we read yx and we just store that symbols in a stack? So and then we start popping them one by one. So whatever pops will be x reverse, y reverse.
That is true, but
And
you
then
should not use the stack to store the input. The stack has some other purpose.
okay.
Right? You should not. If you are given another stack, of course you can do it.
Like, can we use multiple stacks? Like the output of the first thing is stored in one stack, and then we read it and then store it in another stack.
Only one stack.
Oh,
If you give two stack, it becomes as powerful as a Turing machine.
okay, sir.
Stack machine is exactly, equivalent to a Turing machine. It's no longer a PDA. Okay, so I think let us stop. You have other classes, right? Possibly. Anyway, so you try to use this construction on these examples and you will find out.
Sir, could you please explain this part of the construction one more? I mean, if when the separator is exposed, we are the next symbol we are inserting, we are also inserting it below the separator.
Yeah, the separator is this lead is exposed, and for the working of M at this part requires some symbol on the top of the stack. But if the separator is exposed, that symbol is not available. So this AM guesses that that symbol will be B because the transition rule says B is required on the top of the stack. Okay. So B is guessed. Once B is guessed, that guess is stored below the lead. And so it's essentially nothing but replacing this by B, this B. Okay, that can be done. Okay. Now it sees B on the top of the stack, so it can proceed exactly as M does. And at some point of time, it non-deterministically switches to the verification mode. Okay. So the point is that the machine sees B here on the top of the stack. Why? Because it was introduced in the stack in this phase. There is no other way, right?
Yes, sir.
Okay. Therefore, in this stage, somewhere B will be introduced. And then if you replace the lead momentarily, that B and that B, they will collide. Okay. So you may think of this. This is the hint given in our Cosen's book. So this you can think about antimatter. Above the lead matter, below the lead antimatter. So if you remove this lead, this matter and antimatter, they cancel each other. And then once again you put this lead. And this way you validate. Anyway, you try on these examples. Otherwise, it will not be clear.
No, sir. I mean, the construction itself is seems confusing.
Yeah, that's okay. Why?
Sir, what is A and B? Are these
This
arbitrary
is some
symbols?
stack symbols, some stack symbols, which this machine M automatically finds because it has read X. But N does not have this, I would say, opportunity because it starts with an empty, I mean, just with the bottom marker. Okay. And this part is missing, so this is missing. So it will guess these stack symbols one by one. So AB are stack symbols. And it will remember this below this separator. And these stack symbols are generated here. Okay. So it's like this. So when it switches to this mode, it will imitate the operation of M. So if a new stack symbol is generated, it will momentarily, I would say, open the lid. And if this thing and this thing match, then it removes one guess. Again, it puts back that lid. And keep on doing this. Okay, so maybe I request you to do on this. If the construction is still not clear, maybe sometime later I will just show you how it works on this or this. Okay. Okay, it's 9:09. So you don't have another class now?
Sir, no test.
I don't, but I think some people do.
So I think we should stop. Okay. So maybe in the next class or in the next tutorial, I will just demonstrate this construction on this. Okay. Then you will be happy. Okay.
Okay, sir. Thank you, sir.
Thank you, sir.
So bye.
Thank you, sir.